Hello everyone, this is Professor Roman. Let's continue the field theory lectures. We have seen that every field F has an algebraic closure, which I can denote by F bar, and it follows that for any family script P of non-constant polynomials over F, there is an extension of F over which the family splits. And by saying the family splits, I mean, of course, that every member of the family splits. The most important such extension is a minimal such extension. So that leads to this definition. Let script P be a family of polynomials, non-constant polynomials, over a field F. A splitting field for script P, for the family, is a minimal extension field, S, of F, over which the family splits. And just for convenience, I'm going to say that the extension Fs is a splitting field extension for the family P. Suppose that Fe is a field extension, and that a family script P of non-constant polynomials splits over E. And we always know that's possible because we can take E to be an algebraic closure of F. Then E contains a complete root set, which I'll call R, for the family P. And I'm going to leave it to you to show that F with R adjoined is the unique splitting field for the family P that is contained in E. And so, theorem, let P be a family of non-constant polynomials over a field F, then any algebraic closure, F bar of F, contains a unique splitting field for the family. With a discussion of a theorem known as the theorem of the primitive element. And this theorem tells us that if we have a field extension, Fe, that is both finite and separable, then it must be simple, generated by a single element. E is generated by a single element over F. And in some cases, many cases, it tells us how to find, at least in theory, a primitive element. You'll see why I say at least in theory in a minute or two. So, in particular, all finite extensions over finite fields or fields of characteristic 0 are simple. And we can actually strengthen this a little bit, and I'll describe that in the theorem. So, for finite base fields, if F is a finite field, then any finite extension, Fe, is simple. And in fact, that's really a one-sentence proof because E star is cyclic, generated by a single element. The group E star is generated by, say, alpha, and therefore the field E is generated by alpha over F. The term generated is being used here in two different ways, group and field. For infinite fields, infinite base fields, an extension of the form F to F with alpha and beta adjoined, where alpha is separable over F, so it's algebraic and its minimal polynomial has no multiple roots. Beta is merely algebraic over F, such an extension is simple. Moreover, if we take the root sets of the minimal polynomial of alpha, say that's r sub alpha, and the minimal polynomial of beta, so that's this root set, then f with alpha and beta adjoined is equal to f with a alpha plus beta adjoined for any a in f satisfying this condition. A cannot be equal to these quotients. Well, since the field F is assumed to be infinite, but there's only a finite number of these quotients, there are infinitely many primitive elements of this form. And all you have to do is choose an A that fits this condition. So now you can see why I said this theorem gives us primitive elements, at least in theory, because the problem is, how do you find the root sets of the two minimal polynomials? That can be very difficult or impossible. Also, for any extension of this form, where all but the last element here, generator, is separable, the last one is algebraic, so this is a generalization of what we just talked about. This will be simple, and there will be infinitely many primitive elements of this form. How do you find those? Well, the way to do it is to use this part of the theorem and build primitive elements one step at a time by repeatedly applying this algorithm. And I'll leave that for you to look into if you're interested. Okay. But let's take a look at the proof. I already gave essentially the proof of part one because it's just the fact that E star is cyclic. For part 2a, so that is this field extension, the place to look for a primitive element is among the F-linear combinations of alpha and beta. A primitive element is going to have to involve both alpha and beta. And so the coefficients A and B would have to be non-zero. So that's just a guess right now that that's a good place to look. But notice that if A alpha plus B beta is primitive, then we can multiply by B inverse because B is a non-zero element of the base field, and we'll have another primitive element. And so that turns the coefficient of beta into 1. So we can restrict our attention just to A alpha plus beta, where A is, we have to find an element A in the base field that makes this primitive. This will be primitive for this field if and only if alpha belongs to F with this element adjoined. Because if alpha does belong to that field, that's equivalent to saying that both alpha and beta belong to the field, and that's equivalent to saying that this equation holds. And so this field is primitive, and this is a primitive element. This field is simple extension, and this is the primitive element. I'm going to, just to cut down on some of the symbolism, I'm going to denote this field by F sub A. So we would like to show that there are infinitely many values of little a in F for which alpha belongs to this field, each of which then would be a primitive element. Well, A alpha plus beta would be primitive. Now alpha is a simple root of its minimal polynomial because we're assuming alpha is separable. And instead of thinking of this polynomial as having base field f, we are free to choose a base field that contains f, so we'll choose f sub a. So this we'll think of as a polynomial over f sub a, and you'll see why in just a moment. But alpha is also a root of this polynomial. This is the minimal polynomial of beta, where I replaced x by ax plus beta minus a alpha. And I'm calling this h sub a of x. This is a polynomial with base field f sub a, and no smaller. So that's why I upgraded the base field here. So both these polynomials have the same base field for our discussion. Now if you notice here that when you substitute x equals alpha, the a alpha terms cancel, and you have the minimal polynomial of beta evaluated at beta, and that's 0. So alpha is a root of this polynomial. We can put this another way. X minus alpha, but no higher power of x minus alpha, is a common factor of these two polynomials. That's why we need separability of alpha, so that quantity x minus alpha squared is not a common factor. We're guaranteed that x minus alpha is a simple common factor of these two polynomials. So if we can choose a and f so that these two polynomials have no other common roots in any extension, in particular in an algebraic closure, it will follow that the only common factor of these two polynomials is x minus alpha, and so the GCD, the greatest common divisor of these two polynomials, is x minus alpha. And the point here is that greatest common divisors are field independent, which means they belong, the coefficients belong to any field that contains the coefficients of the two polynomials. F sub a is our base field now for these two polynomials, so x minus alpha is a polynomial over the base field, which means alpha is in f sub a. It's a very tricky argument, well, I probably shouldn't say tricky, a very interesting argument, okay, subtle argument. Well, the roots of h sub a of x are the values of x for which this equation holds. Oh, I'm sorry. Okay. The roots of HA of x are the values of x for which this equation holds. If you look again at the definition of h sub a of x, you'll get 0 if that expression is equal to any of the roots of this polynomial, any of the beta sub k's. So all we need to do is choose little a and f so that none of the roots of the other polynomial, the minimal polynomial of alpha, satisfy this equation. Then there'll be no other common roots. So all we need to do is solve this for a and put a not equal sign there, and we're done. Any a in f that satisfies this equation for the entire ranges here will give us a primitive element, a alpha plus beta. For the other part of this, part 2 here, part 2b, we can use induction on n. When n is 1, if you recall, we have n plus 1 elements here in the statement of the theorem. When n is 1, we have one separable and one algebraic element, so we are under the previous situation here, the previous case. So the basis step for the induction we just took care of. So we can assume the result holds for a given value n bigger than or equal to 1, and we now have an additional alpha, so alpha 1 through alpha n plus 1 are separable over f, and alpha n plus 2 is algebraic over f. Well, the inductive hypothesis tells us that there are infinitely many elements of this form, linear combinations of the alpha 1 through alpha n plus 1, not including the last one, for which f with alpha 1 through alpha n plus 1 adjoined has this form, is simple, and this is a primitive element. And I'll call this gamma, and so if I include now alpha n plus 2, then, and by the way, again, this is critical, gamma is separable because each of alpha 1 through alpha n plus 1 is separable. All the a's are separable, so gamma is separable. So we can write this field in this form, and now we can apply the first part of this to A, telling us there are infinitely many primitive elements for the full field here of the form A gamma plus alpha n plus 2, which is in fact this linear combination of all the alphas. I'm guessing that you may need to go over this theorem a few times, the proof anyway. It's a fairly complex theorem. Corollary, any finite separable extension is simple. Any finite extension of a field of characteristic 0 is simple. So if in your study of field theory, which I think may happen in some elementary cases, the assumption is made that all fields have characteristic 0, that eliminates finite fields and more anomalous fields, but it does include most of the well-known fields. Then finite extensions and simple extensions are equivalent concepts. Okay. Every finite extension of a finite field is simple. That was part of the previous theorem, actually. Example. Consider this extension, the rationals q with I and square root of 2 adjoined. The minimal polynomial of I over q is x squared plus 1. The minimal polynomial of square root of 2 over q is x squared minus 2. So the root sets are easy to find. For I, it is I and negative I. For square root of 2, it's square root of 2 and negative square root of 2. Everything here is separable because we're dealing with a field of characteristic 0. So the theorem implies that A alpha plus beta, which is AI plus square root of 2, is primitive provided that A is not equal to 0 or square root of 2 times I. So we can pick A equals 1, for instance, and we get this. So Q with I and square root of 2 adjoined is the same as Q with I plus square root of 2 adjoined. Well, we spent considerable time talking about algebraic extensions of various types. Let's take a brief look now at transcendental extensions. Transcendental extensions are not distinguished, but they do have some of the properties required for distinguishability. Since the class of algebraic extensions is strongly distinguished, it follows that in a tower such as this, the full extension, Fe, is transcendental if and only if at least one of the steps is transcendental. And I'll let you prove that. It's pretty straightforward. This is, however, the best we can do. So, for example, if T is transcendental over a field F, and we look at this tower, the full extension is transcendental, but the upper step is algebraic because little t satisfies this polynomial over f with t squared adjoined. So the full extension transcendental does not force both steps to be transcendental, only at least one step. The lifting property fails. And to see that, all we have to do is take this, if little t again is transcendental, and we lift this extension by f with t squared adjoined, we get this extension, which again is algebraic. So lifting a transcendental extension can result in an algebraic extension. Transcendental extensions are closed under arbitrary composites, because if we have a family of field extensions, and even if a single one of these, say FEK, is transcendental, then EK contains a transcendental element, and that's going to appear in the composite, and so this is transcendental. So that's even a stronger form of closure under composites. All it takes is a single transcendental extension in the family to make this extension transcendental. So here is a summary of those facts. Now, let's suppose again that f with t adjoined is transcendental. We know that f with t adjoined is the field of all rational functions in T. So f and g are polynomials over the base field, and g of x is not the zero polynomial. The transcendence of T, the fact that T is transcendental, implies we cannot simplify this description as we can in the case of T being algebraic. We can simplify to just polynomials using the minimal polynomial, if you recall. No such simplification is possible here. And here's a formal statement. Again, Fe is extension, T and E is transcendental over F. This field, F with T adjoined, is in fact isomorphic to the field f of x of all rational functions in a single variable x. So, in effect then, t acts just like an independent variable. Specifically, this function, phi sub t, that substitutes t for x, is an isomorphism. Also, if little s is an element of f with t adjoined that doesn't lie in the base field f, so say s is f of t over g of t, it belongs to f with t adjoined but not the base field, we can assume that f and g are relatively prime by canceling any common factors. Then in this tower, f with s adjoined is an intermediate field. The lower step is transcendental and the upper step is algebraic. And in fact, we even have the formula for the degree of the upper step. It's the maximum of the degrees of the numerator and denominator of S. So this tells us that every element of F with T adjoined that's not in the base field is transcendental over F. In a simple transcendental extension, all the elements that are not in the base field are transcendental. Elements in the base field are algebraic over the base field, so this is all the elements that could be transcendental are transcendental. As to proof, for part 1, this map is substitution of T for X is easily seen to be a ring homomorphism, and I'll let you do that yourself. It's certainly surjective. It's injective because if an image, f of t over g of t, is 0, then f of t is 0, and that implies that f of x must be the 0 polynomial, because otherwise t would be algebraic over f, which it's not. It's worth pausing a moment to make sure you keep the distinction between a 0 polynomial and a polynomial that's the 0 function. They're not the same thing. For part 2, we take a look at this polynomial, p of x equals g of x s minus f of x. Now this polynomial in X has base field F with S adjoined. T is a root of P of X because G of T S minus F of T is 0. Okay. So T is algebraic over this field. So this upper step is algebraic. The lower step has to be then transcendental because the full extension is transcendental. Since this is not the transcendental, lower step's transcendental, upper step is algebraic. To see that P of x here is irreducible over F with S adjoined, we need to do a little work. That will tell us, that will give us this degree formula. Okay. So first, note that since S is transcendental over F, F with S adjoined is isomorphic to F with Y adjoined, where Y is an independent variable. I could have just said we can treat S as an independent variable, but I decided this would be a little more formal and appropriate. So F with S adjoined here, the polynomial ring over that field, F with S adjoined, is isomorphic to the polynomial field over the polynomial ring over this field, F with Y adjoined. So it is sufficient then, because of the isomorphism, to show that this polynomial, h of x, which is just like p of x, except I've replaced s by y, that this is irreducible over f with y adjoined. Okay. Now, f with y adjoined, this is the field of quotients of the unique factorization domain. This is f square bracket y, the polynomials in y over f. So another way to say this in reverse is the unique factorization is the field of quotients of a polynomial ring is the field of rational functions in that variable. Now we proved in the ring theory course that a polynomial over this field, the field of quotients, is irreducible over that field if and only if it is degree-wise irreducible over f square bracket y, this ring. Okay. So what we can do is we can think of this polynomial as a polynomial in two variables belonging to this polynomial ring, which is the same as this, which is the same as this. And what we have to show is that if this polynomial factors over f with x and y, this is f square bracket xy, then one of these factors has to be constant in x. Our degree-wise irreducibility is with respect to x. Okay. So, if we take this polynomial, where did it go? H of xy. Well, I've added y here because y is now a variable. This polynomial, and it has a factorization, and we'll write out this factorization. This is a polynomial in x and y. We'll write it out as a polynomial in y with coefficients that are polynomials in x. Same thing here. Since the left side here is linear in y, one of these factors has to be constant in y, and the other has to be linear in y. And it doesn't matter which is which. There's a symmetry here, so we can assume u of xy is just a polynomial in x, and v of xy is linear in y. And so this polynomial is now constant in y times linear in y, which we can distribute here. And so c naught of x divides both g of x and f of x when we compare coefficients of y. Therefore, c naught of x, which is the first factor, u of xy, has to lie in the base field. It is constant with respect to x, okay, and y, but in particular with respect to x, and that's what we wanted. This is a subtle argument. It may take a few readings before it becomes reasonably clear. Finally, part one of the previous theorem can be generalized. If Fe is a field extension and we have a set of elements of E, and each element of this set is transcendental over F with the other elements of T adjoined. That's important. Not just over F, but over F with the other elements of T adjoined. Then if we take a set of formal symbols, or another way to say it, a set of independent variables, same size as the set T. So I used the same index set. Then we have the substitution map. Replace any given x with a T. With the same index. This is, again, a ring isomorphism. And so F with this set T of independent variables adjoined is essentially just a set of rational functions in a set of the same size, same cardinality. And that justifies the use of the term set of independent variables for the set T. And the proof, which I'll let you look at, is the same essentially. It's a generalization of the one I gave you a few minutes ago. All right, so that concludes, as you can see here, Chapter 1. And in the next lecture, we'll move on to Chapter 2, which concerns embeddings, field embeddings, and their extensions.